Hello and welcome to the lecture series on principles of electrical engineering. In this lecture, we will be taking an example of DC circuit and try to reduce it with the help of Thevenin's theorem. So before taking up the example, let me quickly state what is Thevenin's theorem. So consider a DC network having various passive elements, okay, and active sources, and it is connected to a load resistance. This could be converted into an equivalent circuit with a battery, let me represent it by VTH, in series with a resistance, let me call it RTH, and this is the load resistance. So the network has been replaced by a battery in series with RTH. So this greatly reduces our effort in solving the circuit, especially when RL is a variable. So let me take up one example and try to solve it with the help of uh, Thevenin's theorem. So I am considering an electrical circuit which is having a battery, then there is a resistance, uh, multiple resistances are there, okay, and again we have a battery here. So this resistance is of 3 ohms, this is of 5 ohms, this is again 3 ohms, this is 2 ohms, and this is again 2 ohm. This battery on the left side is of 30 volts and on the right side is 20 volts. So basically we would be reducing this circuit to this form. One more thing, I am basically taking the load resistance to be 5 ohm. Please remember, we can take any of these resistances to be load resistance. For this problem, I am taking the 5 ohm resistance to be the load resistance. So I have to find out the Thevenin equivalent around that 5 ohm resistor. So we have to replace this circuit by VTH and RTH in series with the 5 ohm resistor. So our problem is reduced to finding VTH and RTH. So let us quickly note down the steps that are involved in reducing the circuit to its Thevenin's equivalent. So the first step is replacing the first step is basically to find out RTH. Okay, so in that, replacing the active sources by their internal impedance or resistance. Since we are considering a DC circuit, so I'm writing resistance here. So a battery would be replaced by a short circuit, okay, and a current source would be replaced by an open circuit. In this problem we have got batteries, so we'll be replacing them by short circuit. And moreover, in the first step also we have to remove the load resistance, that is the 5 ohm resistance. Remove the 5 ohm load resistance, and we have to find out the equivalent resistance between these 2 points. Let me call it this point as A and this point as B. So we have to find out R A B, which will be equals to RTH. Okay, then the next step is finding VTH. And what we have to do it? we have to basically keep the active sources in their place. Okay, and I have to remove the load resistance. In this step also I have to remove the load resistance, which is 5 ohm in our case. Okay, VTH, remove the load resistance, which is 5 ohm in our case. And then we have to find out the voltage that will appear across the terminal A and B. Okay, so I hope it is clear. So now let me start doing the problem. Okay, so let me take a new slide. So the first step was to find out RTH. So to find out RTH, what you have to do, you have to replace the battery by short circuit, by a short circuit. Keep the resistances in their place, and I also have to remove the the 5 ohm resistor. Okay, and here also I am replacing the battery with a short circuit. So this was 3 ohm, this was also 3 ohm, this is 2 ohm, and this is 2 ohm. Sorry, this is also 2 ohms. Okay, this is 2 ohms. Okay, so this point is A and this point is A and this point is B. Let us try to find out the equivalent resistance between point A and B. So this is our A. There are two bifurcations here. So one is 3 ohm, then the other one is 2 ohm. Then they are connecting, and then at this point or this point, then there is again a bifurcation here, and they are again connecting, and this is point B. This is again 3 ohms and this is 2 ohms. So we can easily find out the equivalent resistance between point A and B. So here these two resistances are in parallel, so we can write down equivalent resistance here. It is 3 into 2 divided by 3 plus 2, and then it is in series with, again here also 3 into 2 divided by 3 plus 2. Okay, so this is your RAB, and this will also be equals to RTH. So this is equal to 3 into 2 is 6 by 5 plus 6 by 5, so which will come out to be 12 by 5. Okay, so this much ohms. So this is your equivalent resistance, which we call Thevenin's equivalent resistance. Now let us try to find out the voltage difference between the point A and point B. Okay, so there is a battery here also. This was 30 volt, this was 20 volt, and this was 3 ohms, this is 2 ohm, this is again 3 ohm, this is 2 ohm, and this is point A, this is point A and this is point B. Okay, so we have to find out VAB. So you could see here I can easily find out current flowing in these two branches, isn't it? So the current flowing here would be 30 divided by sum of these two resistances, that is 3 plus 2, and this will give you 30 divided by 5, 6 amperes. So here 6 amperes current flow. On the right side we have 20 volts divided by again 3 plus 2, so this will give you 20 divided by 5 is 4 amperes. So this is 4 amperes. Now in order to find out the potential between point A and B, we start from this point. So I write VA. I can basically write down the KVL from this point to this point. Okay, from point A to point B. So I have to take into consideration the voltage drops that will be at 2 ohm resistor here and 2 ohm resistor here. So VA minus, why I'm writing minus, because I'm moving from A and going to B. So I have to trace my direction. I have to take my direction along the direction of flow of current. So that is why I'm taking minus sign here. So that is the sign convention basically. If you are moving along the direction of current, then you have to take minus. The voltage drop should be minus. And if you are moving against the direction of the flow of current, then you have to take the voltage drop as plus. Okay, so VA minus 6 into 2. 2 is the resistance. Then plus, we are coming to this point. So here the current flowing is 4 amperes, and since we are tracing against the flow of current, so 4 into 2, and this will finally be equal to VB. So VA minus VB is equal to 12 minus 8, so 4 volts. Fine. So, and this is also equals to VTH. So we have found out VTH, which is 4 volts, and we have also found out RTH, which is 12 by 5. So let me draw the equivalent circuit here. So this is VTH 4 volts, and this is RTH, which is 12 by 5 ohms, and this is your 5 ohm resistor. And now we can find out the current flowing through the 5 ohm resistor. Let me call it IL. So IL is equal to 4 divided by 12 by 5 plus 5. Okay, simple KVL. So 4, finally you will get 4 into 5 divided by 12 plus 25. So this will give you 20 divided by 37 amperes. So this much amount of current will be flowing through the 5 ohm resistor. So I hope you have understood how we arrived at the equivalent circuit of Thevenin's equivalent circuit for a given DC network. Please remember, we can apply uh, this same concept for an AC circuit also. Okay, but the only difference is that we have to take into consideration the quantities in their phasor form. The current, the voltages, the drops, they should be in phasor form. Okay, uh, and one more thing that I would like to tell you here. Is that we are applying this theorem, Thevenin's theorem, to reduce our circuit. Okay, so you can see that we have reduced, reduced the circuit. Now it consists only of a battery and 2 resistances. Okay, so especially when the load resistance is variable, okay, we can easily find out different values of load current just by changing this 5 ohm resistance. While if I try to solve the circuit, uh, then and if the resistance is changing, the load resistance is changing, then I have to solve it again and again, and it is a bit difficult if I'm not applying the Thevenin's theorem. Okay, so thank you.